Okay, my job is an impossible one. If you read the title, the Psychophysics years, 1972 to 1982. History is quite remarkable sometimes. I came to NYU as a graduate student in the fall of 1972, not at all knowing what to expect. And I actually came with the encouragement of a physiologist at NYU, Sam Feldman. And Sam and I had a few discussions, and he was wise enough to realize that I would fit much better with Jean-Claude Falmagne, who I'd not heard of. So I met with Jean-Claude, and I think we hit it off sufficiently well that we both gave it a shot, and as I say, the rest is history. Let me say that I was on my own in New York. First time, still a bit wet behind the ears, came from a much smaller town in Australia, namely Adelaide, which these days has a population of just over 1 million, but then it was probably more on the order of 600,000. It was, you know, a capital city, but nothing like the 8 million plus in New York. Jean-Claude took me in and made me feel very, very welcome. He opened his home to me. I spent many hours sitting in his apartment chatting, and simply it was for me a home away from home, and I will always remember that and always appreciate that very much. We began we began work that ultimately led to the publication of Jean-Claude's text monograph called Elements of Psychophysics. And at that time, I knew very little about psychophysics or anything else in experimental psychology. But I had good teachers. Jean-Claude, of course, is actually a superb teacher, and probably that is not always recognized by his students. But if you listen carefully, you learn a great deal. And one very important thing that you learn is to recognize and embrace good scientific taste. I had other good teachers, Murray Glanzer, George Sperling, and I could go on, but mainly I worked with Jean-Claude, and he was the one, of course, who had the vision. He knew where he was going. It wasn't always clear that I did. But over the years, I think we broached some very interesting topics that remain of interest in these days, even in contemporary cognitive science, as we now call ourselves. I was also there, interestingly, in the early 80s when his focus shifted from the psychophysics to knowledge spaces. And that transition was very interesting for me to witness. I didn't play much of a role in it. Over the years, I've kept more or less in contact with people at Alex. I've worked with them casually. And I use Alex as part of my undergraduate stat pedagogy, and it works very well. Students like it, and interestingly, they are willing to spend many, many hours, and I'm talking about over a 10-week period. It's not unusual for students to spend by themselves, on their own and on their own initiative, 100+ hours on Alex. You could never get them to do that kind of work without the environment of sitting at home and enjoying the challenge of conquering the various problem types that they're presented with by the Alex system. Back to the psychophysics years. Well, there is this text, and it's gone through a second printing. It's in paperback, and by my own reckonings, it's been a huge success. And I'll talk about some of those, some of the content of Jean-Claude's text. It's remarkable that there's been nothing like it before or, frankly, since. It demonstrates the importance of inequality constraints. It doesn't, in its present version, talk about how to test those constraints statistically, but that is a topic that together we began talking about in the late 80s, and we published what I think is a basic paper on that topic, and I'll briefly mention that later on. There is a chapter on functional equations. My goodness me. Who, except Jean-Claude, would see the incredible importance of functional equations for psychophysics? And then finally, I will emphasize very briefly the importance of what we called at the time homogeneity laws, and what more recently I have called similarity, or the property of similar functions. Inequalities arise from measurement theoretic considerations. They also arise in other contexts from different kinds of theories. I will talk about a paper that's very beautiful, written by Jean-Claude on random utility representations, where one is not representing objects by numbers, which is more of a characteristic of traditional measurement theory, but by random variables. And that theory leads to a very elegant chain of inequalities that in later work with Don Bamber in signal detection I recognized those same inequalities were appearing, but from a totally different, well, a somewhat different viewpoint. And there they involve expected values, and they amount to a famous theorem by Hausdorff on the possibility of reconstructing the distribution of a random variable from the knowledge of its moments. Then there are inequalities from data, and I've long held that data are very, very often best understood and certainly best remembered in the form of inequalities. You have various groups of subjects like young and old, and you introduce some manipulation that affects both groups, possibly in the same direction, but let's say young more than old. And all of these words that I'm using all express ordinal or inequality constraints. People don't look at things that way. And recently there has been something of a little storm in a teacup concerning the notion of interactions, especially in simple 2x2 designs, and when you can transform away the interaction and when you can't. And the terminology that has been adopted since Geoff Loftus is in my view, unfortunate. The term uninterpretable is used. When is an interaction interpretable and when it is uninterpretable? And I don't find that very useful terminology, but that's the way people think about it. And so let's just talk briefly about some inequalities from measurement theory. I'm not going to go into any details. The terminology for most of you is well known. You know what I'm talking about. In additive conjoint measurement, a necessary condition for an additive representation is a famous inequality constraint called double cancellation. Likewise, in discrimination, models for simple discrimination of stimuli, the quadruple condition and the closely related bicancellation condition are key. The random utility theory that I mentioned dates back to work by the economists Bloch and Marshak, so that there was already a theoretical investigation of such models. What Jean-Claude was able to do was to lay out a chain, an infinite chain of inequalities. The basic probability PA, cap B simply means the probability of choosing from a set B the particular element A. And the chain of inequalities is, in its structure, is very much like the inclusion-exclusion formula from probability theory. The remarkable thing is that Jean-Claude was able to prove that this infinite chain of inequalities was not only necessary, but it was also sufficient. And the sufficiency is just absolutely key, and it's what makes, in my view, this result very, very pretty. As I also mentioned, Don Bamber and I wrote a paper together on the occasion of Duncan Luce's 70th birthday. And in that paper, we connected yes-no data, which from signal detection, which generates receiver operating characteristics, ROC, to corresponding forced choice paradigms. And the probabilities that we focused on were forced choice paradigms involving k+1 intervals in which a single copy of the stimulus is embedded in with k independent copies of noise. And within the context of the normal signal detection theory, the probability of correctly identifying the signal in the presence of k independent copies of noise is simply the probability that the effect of the signal random variable dominates that of the various noise foils. And as you vary the number of intervals k, you generate a chain of inequalities that looks in its structure exactly like the more general inequalities that Jean-Claude had obtained earlier. And they are. This is a special particular case. What's nice about these inequalities is that they express themselves as inequalities governing moments of the signal random variable. And when you look at things in that light, this chain of inequalities is well known in probability theory and is often connected to the name Hausdorff, who showed that if a random variable is concentrated on a finite interval, these inequalities must hold amongst the moments of that random variable, and moreover, they suffice to completely reconstruct the distribution. So in our terms, if you carry out a long sequence of these forced choice experiments and estimate very precisely the probability correct in each case, you can reconstruct the underlying random variable, the signal random variable. And we looked at that problem and we gave multiple examples. I'm not going to go into the business of interpreting data using inequalities. For me, it's just very, very natural. Most recently, I've been interested in this debate on interactions. And many of the issues, many of the problems disappear if you look at, if you interpret data in order-restricted terms. This is not done traditionally. Rather, the language of linear models, analysis of variance, dominates. But that is not a particularly happy language for dealing with the issue of when you can or cannot transform inequalities away. The business of testing inequality constraints comes up in applications of measurement theory and other modeling ideas in actual data. And this is a topic that Jean-Claude and I came across on many, many occasions. It turns out that about 1972, I didn't know about it, and I don't think Jean-Claude did either at the time, the first textbook from the statistical literature appeared, showing how one could go about testing inequality constraints. We finally discovered this text in the late 70s and early 80s. And began with first a classification of measurement theoretic type models, the kind of parameter spaces that they lead to, and discussed the business of testing those hypotheses. Typical measurement theoretic structures are associated with collections of linear inequalities that give rise to polytopes. And this is a topic that Jean-Paul Doignon will tell us considerably more about later today. The theory that we pursued, Jean-Claude and I pursued, was a frequentist theory. And I think that theory was good enough for us to look at some very important data generated by Amos Tversky in a famous paper entitled Intransitivity of Preference. The data he produced on their face seemed to be very convincing for the existence of strong violations of transitivity. But if you did the, if you look carefully at the data, you discover that the evidence is not nearly so compelling as it was intended to be. And we were able to actually carry out sensible statistical tests of what's called weak stochastic transitivity. And in the majority of cases, not all by any means, we found little evidence for violations of that condition. The frequentist theory is interesting. It's somewhat reminiscent of linear models. After all, one is essentially replacing linear equations with linear inequalities, so it's not surprising that there's a strong overlap in the statistical details. And rather than generate standard ANOVA-type F-tests, or in some cases chi-square tests, the likelihood ratio, which is the typical test statistic used by frequentists, turns out to be a mixture of different F and or different chi-square random variables. But otherwise, everything is familiar. There is a Bayesian theory. I've contributed somewhat to that for handling order restrictions. And that's still, in my view, being developed. But there are a number of very good people who are actively working on that. And that theory is maturing quite rapidly and growing in its scope. So I wouldn't be surprised if in the near future people will become much more comfortable with and familiar with Bayesian technology for handling inequality constraints. The importance of functional equations has been emphasized yesterday. And for me, they are quite ubiquitous. But one has to recognize them. And they are not necessarily delivered to you on a plate. You have to look for them, and when you find them, understand how to deal with them. One of the earliest functional equations in psychophysics is a famous one, and it goes back to the work of Fechner, and it's called Abel's equation. In a more modern view, and this leads to classical solutions that are very reminiscent of the thinking of Fechner in terms of accumulating J and Ds. And you do that by iteration. But in our field, the Fechner type ideas are embedded in an empirical structure that gives rise to a continuum of Abel type equations, and that gives rise to the application of so-called iteration groups. And those ideas were present fairly early on through the work of Michael Levine. And I think Jean-Claude was very sympathetic to that work. It's also an area in which the ordinary methods of the calculus actually can be used with some profit. Let me just give you an example that popped up in somewhat recent exploration of mine on understanding so-called symmetric ROCs. So we're back in signal detection, and one says that an ROC is symmetric if whenever you have a point on the ROC, that is a pair of false alarm and hit probabilities, then there's also another point which is obtained by reflecting about a diagonal. And the reflection is identifying a false alarm rate with the complement of the corresponding hit rate, and similarly for the second coordinate. So these particular ROCs are symmetric in a mirror that's placed on the diagonal. What does that mean? And the answer, or an answer, which I am quite happy with, is that the ROC is symmetric if and only if the complement of the ROC So this function, that I'm just calling lowercase r, unlike an ROC, which is an increasing function sitting typically above the leading diagonal, the function r is decreasing and it sits below. That function is an involution if and only if the ROC is symmetric. Now a function on in this case on the unit interval 0, 1 being an involution, that is to say the composition of the function with itself is the identity, r is its own inverse. That turns out, that is a functional equation. I mean, a function composed with itself equals the identity. How many functions are there that satisfy that, and what do they look like? That's a little problem in the theory of functional equations. And an answer is as follows. Every involution of that form can be represented very simply in terms of a function here called phi that maps the unit interval to an interval of reals containing 0 and symmetric about 0. So if phi of t is in the range, so is its negative. And every involution can be written this way. That turns out to lead to a representation of the ROC itself. That is, involving a random variable that I'm just calling x here. The false alarm rate is the probability that the negative of x dominates some criterion. The hit rate is the probability that x itself dominates the criterion, and the ROC is obtained by eliminating the criterion C. So that when you see an ROC that it happens to be symmetric, you immediately have an underlying representation. You know how to capture that ROC in terms of a signal and a random variable, a signal random variable and a noise random variable that are effectively reflections of one another. And that particular representation, there are many other representations, but that particular one captures the symmetry in a very pleasing way. Let me talk finally about the notion of homogeneity laws and more recently what I call similar functions. Weber's law is a famous, historically famous example of a homogeneity law. If you have two intensities, two physical intensities, x and y, and you generate discrimination probabilities, the probability that x is judged to be louder, brighter, whatever, than y, then Weber's law says that the probability remains unchanged if you uniformly increase the intensities of both stimuli x and y. So replace x by some multiple lambda x, y by the same multiple lambda y, and the choice of x over y in probability remains unchanged. This is a statement of invariance, happens to be false in in actual data. But this is historically an important consideration. It's not badly, especially in some applications in auditory psychophysics, it's not badly violated, but it is systematically violated. When I came to think about my long history with the work and the intellectual contributions of Jean-Claude, I realized that he has trained a large number of graduate students, and it has been my privilege to have collaborated with some of those students. And it turns out that I have collaborated with a half dozen of Jean-Claude's graduate students over the years. The one person that I collaborated with early on at NYU is Misha Pavel. Many of you know Misha. But there are others, and let me just mention a few names. It's a young guy at NYU when I first came, Steve Markovici. Then, of course, Misha. Qingfan Xu, Yongfeng Xu, Chris Dobel, and Charlie Chubb. They are my 6 graduate students. Let me talk about, I'll talk about some work in a moment that Charlie and I did. If you embed a tone, a pure tone, in noise, it is masked, and perceptually it's difficult, if the noise mask is intense enough, it is difficult to detect, or that is hear, the tone. But if you either decrease the level of noise or you increase the level of the tone, it will at some point become quite audible. And it's a characteristic of this so-called partial masking that its audibility, so to speak, the onset is very rapid, so that, for instance, at some level of noise, you don't hear the tone, you increase it a bit, you still don't hear it, you still don't hear it, and when you do, you hear it, and you hear it clearly. So it pops out of the noise at you. Now, one can do experiments in which you match the apparent loudness of this masked tone to a corresponding tone in quiet. And Misha and I carried out those experiments. And they produce, as you vary, so one characteristic is simply plotting the fixing the noise and plotting the function C, which is the level of the matching tone in quiet against the level of the tone in noise. And this gives an increasing function that eventually joins the diagonal, where the noise apparently has no effect at all. And you can do this for different levels of noise. So you can think of noise as being an index on these masking functions. And when Misha and I plotted the data, especially in logarithmic coordinates or decibels, the striking thing is that there appears to be a single function involved. That as you go from one index n to another, that is, as you say, increase noise, the function just copies itself and does so by sliding along a line of parallel to the main diagonal, that is a line of 45 degrees. And we put this empirical observation into a statement of, as follows. It's a statement of homogeneity. But it's really capturing the fact that there is a function that is, and it doesn't matter which of the characteristics you pick as the basic function, but you're just copying this function in a particular way over and over as you go from one level of noise to the other. And I can see that I've missed, there should be an N here. So Misha, being an electrical engineer, brought ideas from that field into our joint work. And one of those ideas was the notion of a gain control representation. And this notion of gain control was commonly used in the construction of amplifiers. What you would like an amplifier to do, at least in some circumstances, is to maintain a fairly stable dynamic range, so that as the signal becomes larger and larger, you want the amplifier to react to that increase in energy and push it back down into a useful range. With that idea, we were able to obtain just two classes of solutions that were compatible with this gain control idea. And they are given here. This one in particular is, in its analytic form, it also shows the gain control idea, where the effect of both signal and noise is captured by this additive combination. But there is another solution. It's a little different. You can see that there's a singularity popping up here, so that whereas the upper class of solutions are well defined for any values of positive values of x, the intensity of the tone in noise, there is a threshold here, so that in order for this matching to take place, be possible, make any sense, the tone must be above a certain level that's dictated by the noise. Now, more recently, I have come to think of homogeneity laws as being providing an example of similar functions. And very simply put, if you have a collection of functions indexed by some label, and here I give two such functions, I and j, we say that they are similar if there are real numbers, alpha and beta, that in general will depend on the choice of I and j, such that the one function, f sub I, say, can be obtained from the function j by scaling its argument, x, by alpha, and scaling its value by beta. So there's an obvious group structure here that I won't dwell on. It's, you have two copies of the standard dilatation group, the group that acts simply by multiplication by a scalar. Here's some work I did with Charlie Chubb. It's part of a much bigger exploration of what happens when you shine lights on surface reflectances that give rise to the perception of color. The one thing that was striking to Charlie and me was the fact that human cone absorption spectra are similar. And here we have plotted very accurately determined cone spectra determined by the physiologists Stockman and Sharp. And notice that the axis is not wavelength, but the logarithm of wavelength. Also, these spectra, as is customary in color vision, have been normalized so that their peak intensities are all at 1. That's a device. That's not biology. Biology would have different. This guy would be sitting way down here, for example. So, because of the logarithmic axis, similarity means that these are just translates of one another. Pick up one curve and move it, let's say the medium wavelength cone, and move it a bit to the right, and it superimposes on the long wavelength profile. Likewise, if you shift it to the left, it superimposes on the short wavelength. Now, I don't know, I don't understand why this is. Something like it had been speculated for many years in the color vision literature. But nobody seemed to have had the right, exactly the right way of looking at things. But this is clearly a good way to look at things. If you look at the actual molecules involved, they're horrendous. And so I don't understand why something so simple should come out of very large nucleic acids. There are multiple nucleic acids involved, and they all have to cooperate with one another in a way that comes out with this very simple fact. The remarkable thing is, once you realize that the cones are similar one to another, then you can ask, what happens when you shine particular lights, especially daylights, on colored pieces of paper? And Charlie and I numerically explored this, and I don't want to talk about that, that more general work here, but rather to talk about a single problem, which is perhaps the simplest of all problems. Suppose you shine daylights on a white piece of paper, which ideally has a flat, uniform reflectance spectrum over the visible range.
I have a question.
Yeah.
You know, it seems to me that it's the action spectra that should be similar, not the absorption spectrum. That is, the action spectrum is the change in absorption due to a photon being absorbed.
These data are obtained literally by shining lights, lasers if you like, monochromatic lights, on a solution containing the relevant photopigment. And part of the light is absorbed by the photopigment, and part of it is transmitted. And what's transmitted is measured, so you know how much has been absorbed. And from that kind of measurement, you obtain these profiles. So at various wavelengths, the L cones are transmitting most at a particular frequency, and that ability falls off each side in this particular way.
The problem with the absorption spectrum is it includes not only the photopigment but other aspects of substance that absorb. That don't change with light. And the action spectrum is the change in absorption.
Yeah.
So just I assume people have tried this sort of the chemical absorption experiment with dyes and pigments that are not the ones that we use in our eyes. And they
Probably, yeah. I don't know a lot about that, but yeah,
But
probably.
They don't, do they or do they not come up with spectra that are similar to this?
Oh. These shapes are characteristic of biological receptors that in the human case we call cones. They're also quite characteristic of the rod system as well. Now, if you are in industry and you're interested in other molecules that also absorb light, you're not going to, as far as I know, you're not going to get similar, I mean, you're not going to get copies of this shape. It'll be some...
So it's something specific to these biomolecules?
Absolutely, yeah, yeah. So there is a rhodopsin template, for example, looks very, very much like this, but rhodopsin is found in rods, but not cones. These are other kinds of opsins. So it's a class of molecules that nature has discovered does a very good, useful job. Now, George, I'm not...
It's not critical for your argument.
No. No, but I mean, in terms of interocular media that definitely have an effect on measured results. Other experiments are used to account for those.
It's the opposite, right? It's
Yeah, you would.
large molecule with all the chromophore in the middle. The only thing that changes
That's
is
right.
the little part of the large molecule.
Right.
And
Yeah.
that's why all these spectra are similar.
Right. Right.
But what
But I don't. I
parts
can't.
of the
Yeah.
molecule that are irrelevant for seeing vision also absorb light. And to cancel that out, you use the action spectrum. And that's
Fine.
what's-
Yeah. Yeah. So back to the particular small problem that was part of the work that I did with Charlie Chubb. Concerns the so-called daylight locus. As the sun travels across the sky from dawn to dusk, it looks different. We all have the experience of dawn and dusk being associated with long wavelength, red appearance, whereas at high noon, with the sun being directly overhead and shining on a piece of white paper, the light that is reflected is very different from that occurred both earlier and later. And the different phases of daylight plotted, measured, and plotted in standard so-called chromaticity coordinates generates a smooth locus called the daylight locus. And in a very rough way, the corresponding colors move from reddish to bluish through white. The CIE, which is a French, an acronym for a French organization, but it is the international organization for light, for vision, has measured and plotted this this curve, and they fit it with, they do a polynomial fit, which contains some arbitrary numbers. It turns out, and these are chromaticity coordinates, here's this very gentle curving daylight locus. Using the similarity of the three cone types, Charlie and I were able to generate a fit to this locus that used absolutely no free parameters. The only input was either the cone profiles themselves or what is equivalent human matching functions. And we used those human matching functions and we generated these predictions that fall exactly on that. And we know the functional form of the curve. It's nothing to do with the polynomial. And it comes out simply by paying attention to this notion of similarity. Here's my last example. It's a psychophysical law of similarity. And the one standard representation for discrimination probabilities involves a difference between two functions, well, the same function u evaluated at different values x, y. And associated with this function, one looks at its level, the corresponding level functions. which are much more interesting. They are what a psychophysicist would measure. So it's the sensitivities that I want to look at. And here is the notion of similarity that I postulate. So it looks a little bit complicated, but one has a system of functions indexed by a variable s, which here is just a real number, and the effect of scaling its argument with a multiplier lambda is to take you from one of these functions to another one that depends both on the initial index and on the multiplier, and multiply by some function of these two variables. It turns out that if you put these two simple ideas together, you can obtain all such families of functions, and you can determine the so-called scale, u of x, in all cases, and that there are 11 different functional forms. We've looked at those functional forms and recognized that many of them have been discovered in special cases before. But it's nice to have the prior, as I said, many of these functions have been recognized earlier and proposed earlier for one thing or another. And here they are, all in the, put in the same context. And the context is one of similarity. Let me wrap things up with that remark. And again, Jean-Claude's influence, to me, is apparent throughout my work. I may never have discussed a particular issue. I don't think I've ever had a discussion, say, involving the work with Charlie Chubb in vision. But I probably would not have noticed or bothered to look for similarity without the earlier work on homogeneity that was initiated by Jean-Claude. And there are many, many other examples that I could give. So Jean-Claude, thank you for being my mentor, a dear colleague, and a dear friend. Yeah.
I have a question about the daylight.
Yeah.
I can see how that would work if we have seasonal changes, that the sun is going to be at a different place and the colors are going to be
Yeah.
season and longitude.
But they all move along, they all are represented by some point along. It's not as though you start.
But you didn't set any parameters, so the curve is going to be different. How do you move the curve? The position on the curve is going to be different.
The position is different.
Only the position.
Yeah. Yeah.
It just depends on how high the sun is.
Yeah.
It just depends on how much atmosphere the sun is.
Absolutely. Yep.
And that doesn't matter where it's, if it's straight up or on the side.
Is it
Let
the
me
same
suggest-
for
let me
all
suggest that,
observers that have the 3 cones?
Sorry.
Is it the same for all observers that have the same cones, even though they might have different maxima? If they have a where you change the peak, are they all going to be identical?
Where's Kimberly when I need her? Sure. There's variation amongst individuals. It's not huge by any means. And can you take the daylight locus and say that it applies to every given individual? Probably
on
not.
The assumption that for every individual, if on your log plot,
Yeah.
that the shapes of the three are identical.
Yeah.
Would that end up?
All I know is if you isolate, okay, you take a cow and remove its eyeball and suck out the photopigment, the rhodopsin, and you measure the spectrum. It looks just like that, but displaced. And that fact, the idea that there's this sort of template for, it's an old idea, and it goes back to Dartnell or someone, and then over the years, the original attempts were to, in my view, incorrectly try to capture this obvious similarity on a wavelength basis. And I think that turns out to be wrong. So you want similarity to involve a multiplier, and so it's natural to look at the logarithmic coordinate, and that produces the translation. Yeah.
Let's have the discussion during the break so that Virginia can get set up.
Yeah, right. Okay, thank you.